Welcome, everyone. Welcome to the first year we're doing this here at the Wilkes Summit. This is a student climate research lightning talks. And so these are fast talks that just sort of summarize a research project in a compelling way. It's a competition, and we're really excited to get this off the ground. So let me talk quick about the format. Today we have 10 presenters. Some of them are undergraduate students, some are graduate students. And each student will present their research project in a 3-minute time span. And we have to stick to that. We have a pretty tight timeline here today. We're starting a little bit late and we have to get all the talks in and then we have to leave time for voting. So each student will have 3 minutes to present and then they'll have 2 minutes of Q&A. I mean, I think for the most part, that may just be like one question often. But if the question's quick, we may go to a second. Okay. After all 10 presentations are complete, we're going to bring all the presenters back up here and have them just sort of link their name to their presentation so everyone can take stock of and remember the presenters. And then we're going to move into voting.
So we won't be able to see it right now, but when we get to the very end, a QR code will come up on the screen. So make sure your device is ready to scan it and sign into the poll. And then you're going to select your 3 preferred presentations and we'll see the results come in live on that, and we'll do a tiebreaker if we need to, but we might not. We'll see. And presenters, I'll be in the back at my computer holding up timing signs. You won't get a 3-minute warning because you start at 3, but you'll get a 1 and then I'll tell you to stop. So just
which is similar to what I saw down at the poster session, right? You just select the 3 that you're most excited about. And we really do need to stick, so let's be responsive to the time because we really have to stick for the sake of fairness and also just staying on schedule. Let's try to stick to the schedule. And with that, we have our first presenter who will be coming up now, Austin Clark.
Anthropogenic climate change is causing an increase in the intensity, frequency, and duration of extreme heat events across the world. Extreme heat events that were rare a few decades ago are now occurring with increased frequency, and heat records are being broken seemingly every year, with the past 10 years being the hottest on record globally. Heat is the leading cause of weather-related fatalities in the United States, causing more deaths over the past 30 years than tornadoes and flooding combined. Studies have shown that while extreme heat can impact all people, it impacts some populations more than others. Many studies have shown that areas with higher levels of ethnic and racial minorities experience greater heat. Conventionally, when looking at heat exposure, we look at the average heat value of a county, census tract, or block group level. While these studies have found inequities in heat exposure based on racial or ethnic minority status, the distribution of heat population within spatial units like counties and census-defined areas can vary dramatically. None of that variation is accounted for in prior research on heat inequities. To advance fundamental knowledge in this area, we are conducting analyses that pair very fine-scale data on heat with microdata from the US Census that includes individual residents' precise home location to assess if people from racial or ethnic minority groups experience unequal exposure to heat in US cities. We are using hexagon 1-meter radiant temperature data created by Dr. Lee at the University of Pennsylvania, along with individual level census microdata from a federal statistical research data center. We are creating buffers around home locations of each individual in 12 cities across the United States. We are calculating the mean high temperature for the hottest month of the year for each of these buffers. We will give each individual person a temperature value. By merging the data with data from the decennial census, the American Community Survey, and the American Housing Survey, we are able to link the temperature data with demographic data. Additionally, we are replicating this analysis at the census tract level to assess how results differ when using the census microdata versus publicly accessible aggregated data. Our goal is to show if there are inequities in heat exposure on an individual and population level. While we do not yet have results, we are expecting to find more pronounced inequities when we use microdata in combination with the high-resolution heat data in comparison to using aggregated data. Thank you.
Questions?
The Heat Expo data that we have gotten from a collaborator has the cities already selected. They're large cities across the United States. Yes. That data is accessible. We're not planning on doing that in this first round, but that's something that would be very interesting to add on later.
Is that? Okay, and next is Riley Gagne. I don't know if I'm pronouncing that correctly. Gagne, okay. You see, yeah, forward, backwards.
Cool. So, hello, I am Riley, and I'm excited to talk about my project, which is polar bear energetics via satellite imagery. So, as you guys probably know, the habitats of polar bears are decreasing as global temperatures rise. And so polar bears are forced to swim more now than they have ever, especially in recent years. And so this is especially problematic because polar bears spend 4 to 5 times more energy swimming than walking on the ice. So there's a lot of long-term effects of that. And so previous work was done by a peer of mine named Nicole Forrester. And so here you can see this array of pixels that are denoted as either water or ice. And so she generated this algorithm that will show you the most energy efficient path. However, the problem with this is that she only had random data. So my role was to kind of put some real life data into this algorithm. So I'm looking primarily in Hudson Bay, Canada. And so I have one area that I've been looking at, which is 100 square kilometers. It's off the coast of Churchill, which is the polar bear capital of the world. So I'm looking at a couple different types, but I'll show kind of an example workflow. So on the left, we have an optical image. And so this is a satellite image, but it's pretty close to what you would see with the naked eye. And so you can see there's kind of some gray areas. And since images are taken at all different types of, all different times of day, the lighting can vary a lot. And so to kind of eliminate a lot of the variability, I'll color enhance it. And then I use a machine learning model to predict which pixels are most likely ice and water. And then finally, I can run this optimal path. So this made me curious about what other kind of characteristics play into the cost of a polar bear traveling. So one thing that I looked at is this concept called Moran's eye. So at a high level, if it's closer to 0, your value, it means that your ice is more spread out and it's more of a uniform distribution. And if it's closer to 1, it means it's a lot more clumped together. So you can imagine that, when it's more evenly distributed, the probability of being next to another ice pixel, to say, is a lot higher, so the cost is lower. And this increases as you get into a lot more big ice flows and there's a lot more water in between. I've also looked at sea ice concentration, and we've seen similar patterns as well, where as ice approaches 100% concentration, meaning it's approaching a sheet of ice, the cost will decrease with kind of like a plateau at around 60% ice. And then similarly, is it just open water, the cost goes up a lot. So it's really exciting to see these results, even though I've only looked at one area that's 100 square kilometers. And it'll be cool to start to pull together, actual tracking of bear data and match the different locations to where they are in the year. So thank you.
Questions?
Yeah. Say it one more time. Sure, so right now it's not, but like I said, over the summer I'm going to work on it and kind of see where the polar bears are going. And my kind of long-term goal is to see, over time in the past 10 years, is the average cost that a polar bear spends on their journey, when they leave Churchill, they go out and come back, has that cost really been increasing? Also, when you take into consideration that the ice is melting sooner and freezing later, so there's less time for the polar bear to actually be on the ice. So to kind of see those two things and how that's modeled.
Okay, congratulations, great.
Thank you.
Okay, up next, Autumn Hartley.
Hi, my name is Autumn Hartley, and today I'll be presenting a preliminary assessment for the potential for carbon storage in the North Atlantic Igneous Province. 66 million years ago, a climate change event that was similar to ours today because of caused by a large proportion of CO2 in the atmosphere happened during the Paleocene-Eocene thermal maximum. The onset of the PETM was around here, and as you can see by this black line, it sharply increased, similar to modern day where we had essentially a vertical increase. The only issue of correlating these two together is that the PETM occurred over 5 million years, and ours has occurred over 175 years. So PETM is on geological timescales, and our current climate crisis is on human timescales. So in order to help our current climate crisis, we need solutions on human timescales, which is where my research comes in. So CO2 sequestration is one of our methods for removing carbon dioxide from the atmosphere. We do this by taking CO2 from the atmosphere, turning it into a CO2-rich fluid, and injecting it into the ground to form mineralized CO2. An actual natural example of this is shown on the left here. This is from the North Atlantic Igneous Province off the coast of Norway in the North Atlantic. This shows a basalt sample that has been reacted with carbonate-rich fluid to form these veins of carbonate. This is solid carbonate, which contains a lot of CO2. This is an inert form, it cannot move around. This is what we want because we don't want fluid moving around. So my first task was to take all of our samples from the NIP and analyze them to find out what other ones might have carbonate in them. How deep is this reaction occurring? We were not able to find any carbonate minerals available inside of these 4 samples that we analyzed. However, we did find a lot of altered minerals and igneous minerals. So now that we know what our samples are full of, we are able to have a better idea of what's going on in the NIP. These are other samples from the North Atlantic Igneous Province, full of very pixelated images, but also vesicles that are filled in basalt. Vesicles are holes in a basalt. They are what you're able to fill with carbon-rich fluid if you inject it and are trying to get rid of it. Next calculations are going to be quantifying the amount of vesicles, holes, fractures, and stuff available for us to inject these carbon-rich fluids in them and expand those calculations to the entirety of the NIP so we know how much space is available in order to address our current climate crisis. Thank you.
Questions?
Yes, so right here we can see filled veins and vesicles. These are things that have already been covered by the minerals we saw on the previous slide, so clays and altered minerals. And we want to quantify how much space of these veins and fractures have already been filled with our material and how much have not been filled. So we would be able to distinguish between filled space and empty space in the North Atlantic Igneous Province and be able to identify reservoirs.
Excellent. Thank you. Okay, Lucy Leary. Greens forward, reds back.
Okay, thank you. Hi, everyone. Thank you all for being here. I just wanted to start by apologizing to whoever speaks after me. I have really clammy hands and the microphone is going to be very sweaty. My name is Lucy. I'm a math student, and I've been researching how power law noise, which is also called colored noise, can impact transient dynamics and ecological modeling. I've been focusing on an herbivore grazer model introduced by May in 1977 with parameter values set by Poulsen, Plunkett, and Reimer in 2024. This is the formula for math nerds. This is what it looks like when it's plotted out, and these are each of the parameters with what they represent. This just generally, it's the plant population as it changes over time. This model has something called a long transient, which is when the plant population hangs out at a seemingly stable size for a long period of time before rapidly transitioning to the true stable population size. Long transients are very common in ecology, and long transients are emerging because of global climate change. Long transients can lead to sudden extinctions, so it's important from a conservation perspective that we learn to recognize and model them accurately. Power law noise is a type of random process that occurs in nature. Climate change is an example of pink noise, which is a positively correlated power law noise. I've been experimenting with adding power law noise to the plant grazer model in different quantities with different correlations and to different parameter values to see if power law noise can ever increase the length of the long transient in the model. We measure this increase using something called the mean first passage time. Historically, mathematical biologists have opted to use white noise in ecological modeling, which is a type of power law noise where beta equals 0, to represent the full range of power law noises that are present in nature, under the assumption that white noise and colored noise have the same effect on the model. We have found that this is not the case. In fact, the different configurations of the type, amount, and location of power law noise in the model can have opposite effects on the model. For example, noise added to the carrying capacity can both shorten and extend the long transient, which is really significant for the future of ecological modeling because it shows us that the way that we choose to apply noise to these models can drastically alter the way that the model behaves. As I said before, this can often lead to sudden extinctions that are really hard for wildlife conservationists to predict. So it is necessary that we learn to model these systems more accurately using power law noise rather than just white noise. Thank you.
Questions?
So climate change is an example of power law noise. It exhibits characteristics of something called pink noise, which is power law noise with a beta value equal to 1. Long transients are emerging in ecology because of climate change, novel long transients in coral reef systems and forest systems. And I won't pull it up, but that was the figure with where we plateau for a really long period of time and then suddenly jump to a new population size. And so that can be dangerous for wildlife conservation if we think that we're in a stable state and we find out that we're in a transient state.
Great, thank you. Okay, Julie Moyano.
All right, so I'm Julie, and I'll be talking about ranchers in Mexico. So as we know, climate-induced multi-year droughts are becoming more frequent, and the rural poor are the first to experience the effects and experience it the hardest because their livelihoods are dependent on the land. And so my research focuses on ranchers in Baja California Sur, Mexico, and how they were impacted by a severe drought from 2020 to 2022. An important distinction I want to make is that these ranchers are subsistence pastoralists, which means that they raise livestock for their own personal use. It is not a large-scale commercial operation. And if they do sell, it's to local farmers markets. And the local ecology of Baja California Sur, it is the part of the North American arid West, and they rely on seasonal hurricanes for their water source. And so what our research aims to do is look at how they adapted to the drought, if they're recovering, and what can be done to improve their resilience. So the ranchers rely on the local ecology for their animals to graze on, and during a drought, they have to purchase feed to supplement their diets. And because this was an extra expense, many ranchers had to sell their assets, take out loans, or either themselves or a family member had to get employment for an extra income. And because of this, they are not recovering. 90% of ranchers have not seen recovery in their herd sizes, and 93% have not seen economic recovery. And ranchers estimate that they can withstand another 2 to 3 years of prolonged drought before they will be forced to abandon their ranches which could ultimately lead to the abandonment of ranching culture. And this is important because ranching is the oldest living tradition in Baja California Sur, Mexico. And it's important to take action now to help improve their resilience to drought so that they can continue to preserve their culture. And especially considering that droughts will only continue to get worse. So these are some recommendations that we have. Ranchers reported their number one need is diversified employment sources so they can secure and have a secure income. Also, they need improved infrastructure to grow and store their own feed, as well as providing assistance to their households with necessities such as electricity, just for their well-being. So yeah, we hope to get this information to some NGOs that we're working with and hopefully also the government.
Thank you. Questions?
Yes, sorry, I think I might have skipped that, but we interviewed 98 ranching households. It's a collaborative team of researchers, so kind of like my mentor, some biologists, even ranchers interviewing other ranchers that have joined the effort. I did one interview when I went there for field school.
Great. Thank you. Okay, Nathan Murphy.
Awesome. This is my satellite telemetry study, and I don't have so much time, so let's just get right into it. These are our study species. On the left, we have the steppe eagle, and it was actually rehabilitated from an illegal market. And they're very rarely caught, so this is a great opportunity to get a tagging study in. It largely inhabits the steppe ecosystem, which is at risk due to land use change and climate change. And there have been no telemetry studies in this flyway since 2014. And they've actually experienced 58% decline over the past 3 generations. So very endangered bird. On the right, we have the booted eagle, which is much smaller. And we caught it in a mist net in September of 21 in eastern Turkey. It inhabits areas such as woodlands, flatlands, agricultural areas, mountain slopes. So it's a lot more adaptable. This is the first telemetry study ever in this region. And they actually have stable populations with about 200,000 mature individuals. So this is what we found. On the left, we have on a map the migratory routes. In red, we have the steppe eagle, and it was tagged in eastern Turkey. This first stopover site was actually at a trash dump. It stayed there for about 20 days, and then it traversed the Arabian Desert and crossed over at a well-known bottleneck at the Suez Canal. And then it navigated through the Nile River Valley, wintering in the Sahel in Sudan. The booted eagle in blue traveled across Saudi Arabia, crossed at Bab al-Mandeb in Yemen, another well-known bottleneck, and it had a stopover in Ethiopia, where it stayed for about 20 days. It wintered in Uganda, in an area where there's lots of agricultural land. Its return very closely mirrored its outgoing route, and it stopped for about 3 days in Iraq in a delta. It bred in Russia, and something cool to note is the steppe eagle took about 35 days on its route before it stopped transmitting. This bird may have been killed or the tag may have fallen off. There's no way to know. But often there are human-induced mortalities in this region. But it did not follow the well-known loop route, which goes through Yemen and then back up through the Suez Canal. This could be because it's moving further north, because it's getting a lot warmer. The booted eagle, this is the first time, so this is foundational data. This is a great way to visualize migration. It's a net displacement figure, complete with stopover sites, migration periods, wintering, breeding, etc. So I could get more into the science, like the fact that the Arabian Desert, as well as the Sahel, is predicted to rise 8 degrees Celsius by 2100, which would be absolutely devastating for these species. But I wanted to get into some other things, like nature's quiet labor. If you look in your own backyard and with binoculars and look in trees, there are birds nesting that have migrated thousands of kilometers, and right among our homes, our cars, and our noise. Movement requires trust. We need to provide that trust for birds by reducing our carbon emissions and restoring habitats, and some perspectives on modern comfort. Sometimes, like, I'll get up in the morning and think, man, I've had no sleep and I have no motivation. But then I think, well, at least I'm not a booted eagle and I have to travel across the Red Sea through a war zone while navigating the risks of falconry and climate change. So these birds have an amazing story. I hope you enjoyed it. Thank you.
Question.
Yeah, so it sends out a signal, and actually the steppe eagle, it's very interesting. There's no access to cellular data in certain war-torn areas, and so the bird did not transmit for like several months, and then it popped up in Sudan. So it sends out a signal and it has to get picked up, and it sends out a signal about every hour or so. So you connect it point to point. Yeah.
Right. Thank you. Okay, Tyler Pack.
Hello, and welcome to my presentation on WRF accuracy during temperature inversions. So the Weather Research and Forecast Model is a numerical weather prediction tool used to simulate weather patterns. My research project focuses on how well WRF perform during temperature inversions. So usually, as you might know, the atmosphere, it gets colder the higher you go. And during temperature inversions, this flips on its side. This warm air layer above the cold air creates a stagnant film, which prevents air circulation from happening. And that causes pollutants to build up and eventually lead to poor air quality. Valleys are especially common for having inversions, and this is what makes Salt Lake a prime spot for temperature inversions. You just need to go outside to figure that out. So there are 4 different configurations in WRF tested. 2 microphysics options, which simulate condensation, precipitation, and cloud formation, and 2 planetary boundary layer options, which simulate how heat, moisture, and momentum move across the surface. Now, here we can go over the model evaluation performance during the inversion. So here shown is the R-squared value, or the Pearson correlation coefficient of each model with the model's name scheme below. And we can see that immediately for temperature that the R-squared values, we have a mean R-squared value of about 0.73 to 0.75 for all 4 schemes, which is pretty similar, showing that temperature remained high in accuracy for our schemes. The last bar represents a summer period with no inversions, representing the ideal case scenario of what our accuracy we would want to be. And as you can see, it isn't much higher than our normal, than during the inversion accuracy. However, we can say it is a little different for wind speed. Wind speed, we have a really low accuracy of about 0.29 to 0.3 for all 4 models, with a jump for our ideal scenario at 0.41. This suggests that during an inversion, our models over-evaluate wind speed, usually by predicting winds when, in other words, there should actually be no winds in a calm atmospheric environment. So what does this tell us? There's no significant difference between the overall accuracy of each scheme during an invasion. We have a possibly slight underperformance in temperature compared to our preferred accuracy, but not enough to make a significant impact. However, there was an underperformance in wind speed accuracy compared to an ideal scenario of a typical summer day. I believe a simpler planetary boundary layer scheme could be tested for possibly increasing the accuracy of the wind speed. The more complicated the scheme, I believe the more wind or turbulence it's modeling that will compound errors and affect the overall accuracy. Next steps, new variables to be tested, like wind direction and humidity among the variables, along with others like sea level pressure and cloud top. Test new scheme combinations and events to get better data and diversify the results and confirm my findings. Thank you.
Excellent. Question?
Mhm. Not shown here, but I did evaluate the root mean square error and bias as well. No, they were all, again, pretty similar. Yes. That's a good question. So honestly, it really depends on how long your exposure to temperature to poor air quality is, and inversions are related to poor air quality. And Salt Lake City is one of the most suspect spots for inversions. I believe it's the second most common place for inversions to happen, with Medford, Oregon being the most common.
All right, thank you very much. Jacob Sussman.
Great. Thank you. My name is Jacob Sussman. I'm excited to share with you some work on modeling valley fever. So valley fever is an underreported fungal infection that's of urgent public health concern. Coccidioides, the valley fever fungus, lives in the soil, and when it's kicked up and inhaled, it causes fungal infection. While there's not comprehensive data on soil sampling of coccidioides in the American West, what we can do is model this based off of cases reported to the CDC of valley fever. We want to do so considering a complex reporting process and better understanding the ecological factors that drive presence. Additionally, it's hypothesized that some burrowing mammals may harbor cocci, which is released upon death and put in the soil. So this is something that offers a unique insight into how the process works that hasn't been explored in modeling approaches. So across the literature, we gathered a list of 16 potential reservoir species that showed some evidence of positivity. A collaborator, Corey Merrow, provided us with species distribution models for each, and then we compiled these and summed them at the county level. So for each county, we have the number of species present that are potential reservoirs. For our actual model, we want to adopt a multi-level approach because we know that there's systematic error in the way that human valley fever cases are reported. For instance, we have this ecological process, but then on the human case level, Texas doesn't report valley fever to the CDC. So this is something we need to account for. So we have one level with our bioclimatic covariates, all of our mammal distributions, and a county spatial effect. And then at the higher level, we have sort of a state reporting effect and a population offset. We run this through a spatial Bayesian inference model called INLA with human case endemicity. This is a binomial model, and then we get a county level probability distribution. So while we're working to refine our approach, we're excited to share what our current model outputs look like. Here on the left, we have the final observation level county probability of endemicity. And so you can see definitely some evidence of state borders here, but it follows from known valley fever human case hotspots. On the right, we have the output from our ecological level. You can see that this is a lot smoother, and it'll be really valuable for from a public health standpoint to understand where these two levels differ. Additionally, we find that our species presence variable is important in the model. It's an effective predictor of endemicity in our model output, and counties with higher presence end up having a higher odds of endemicity. So we hope that our modeling efforts will help us better understand the distribution of coccidioides, especially because a lot of the factors that might drive presence are expected to change as the climate does so as well. Thank you.
Questions?
Yeah. Yeah, so fantastic, an important question. So we have data from the CDC through 2022. They have data from 2023 that'll be used to validate these predictions. So currently we have that we're working with, but it's definitely a concern, especially because if the closest we can get to the true presence is from these approaches that consider human case data, and that's important from a public health standpoint, it's already something we're facing challenges with, and so probably increasingly more so. Yeah. Yeah, so Currently, in sort of alignment with CDC goals, we're focused right now on the American West, but it's a fantastic point because, yeah, the actual fungus we know exists in parts of Mexico and South America, where it's also a pressing global health issue. This is the data we have to kind of better understand it now, but yeah, great question.
Thank you. Okay, Alan Townsend?
Yeah.
There you go.
Okay, thank you everyone for being here. This is going to be the second presentation about pollution and temperature inversions. I hope I can live up to Kyler's presentation. So basically what we focused on is being able to predict PM 2.5 levels in the Salt Lake metropolitan area using a random forest machine learning model. So basically Kyler kind of went over this already, but we experience temperature inversions in Salt Lake City. We have one of the worst pollution in the world because of these inversions. And the culprit of kind of that increased pollution level during these inversions are what's known as cold air pools, which is where these inversions trap pollutants, leading to higher PM 2.5 levels. Now, in order to quantify these cold air pools, we were using two classification metrics. The first one being valley heat deficit, which is a measure of the amount of energy needed to break a temperature inversion. You put that energy in, raise the temperature more towards the ground to break the inversion, as well as classifying caps as yes, no, and maybe. So our goal is to improve PM 2.5 prediction by incorporating these stability metrics, as well as investigating the reasons as to why temperature inversions increase pollution, because it's not really clear-cut. Now, this is the models we developed. We developed 5 different models, as well as a naive model. That naive model is just predicting the previous hour's pollution level and saying that's the current pollution level. And then our other 5 models, we have a meteorological model that's taking in temperature, atmospheric pressure, those kind of metrics. And then 3 other models that are including those caps, cap metrics, and valley heat deficit metrics. When we incorporate those cap metrics, our R-squared jumps to 0.19. It's not great, but it's more than double than just the meteorological data. And then when we incorporate more features that we've engineered, such as rolling mean pollution levels, we see our R-squared increases to about 1, similar to the naive, meaning that pollution level is very autocorrelated. And kind of diving more into, probably hard to see, but kind of the metrics we looked at, this is a SHAP plot. We look at NVHD and then CAP. We see that and pressure are one of the most important features when predicting pollution. And we see high NVHD and high CAP, high pressure, those lead to higher pollution levels. Now, looking more at kind of the models here, we can see these are our previous historic pollution levels, and we can see they dominate the feature importance, kind of suggesting that the model isn't really doing anything. It's kind of just predicting the previous values. But yeah, thank you.
Questions?
I think the most common value is around 50 micrograms per meter cubed is when it becomes a really big problem.
Okay. Do you want to ask a question?
Yeah, that's a really great question. That's kind of the future work we would want to do, is doing more long-term predictions. We're doing more like nowcasting, predicting 1 hour ahead. It'd be interesting to predict, 1 day ahead, 1 week ahead. I'm sure that naive persistent model would completely fail if that was the case. And then we could also implement more models with attention, like an LSTM or a transformer, to kind of predict that.
Thank you very much. Okay, Brant Wynn. It's our final presentation. Green's ahead.
Thank you very much. Okay, so my name is Brant Wynn. I'll be presenting on the water use of native versus invasive plants in riparian zones. So one of the biggest invasive species affecting the desert ecosystems of southern Utah and its riparian zones is Elaeagnus angustifolia, otherwise known as Russian olive. It competes in riparian areas with the native Populus vermontii, the Fremont cottonwood tree. In riparian zones, the areas directly off of waterways and streams, they're critical ecosystems that are highly vulnerable to invasion. Invasive species can decrease biodiversity through differing in plastic physiologies that allow them an advantage in times of stress and in highly vulnerable areas. This allows invasive species to outcompete native species. So that adaptability can potentially cause cascading effects that increase climate change while decreasing the societal value of the land. And so in my research, I believe that Russian olive competes with its native counterpart, the cottonwood tree, for water by having more phenotypic plasticity. So the phenotypic plasticity is the ability of a plant to change its phenotypic expression in response to the environment. There's little empirical data on the physiology of Russian olive trees, so I wanted to test to see if the water use shifted in response to changes in water availability. I hypothesized that Russian olive's water use will be more plastic when compared to cottonwood trees. To test the plasticity of water use in Russian olive, I measured the water potential of both species across the months of June, August, and September, 9 trees of each species. So plants can control their water stress by closing their stomata, meaning there's a variation in how much water stress a plant will allow themselves to face based on the physiology and behavior traits. So to measure plant stress, we use water potential, a measurement that tells us how much tension is present in the plant's vasculature. We use the skull under pressure bomb, pictured there, to measure the water potential of a sample of leaves. So after data were collected, we used the program R to create box and whisker plots to represent our findings. So we took 2 measurements, one before dawn to see if plants are experiencing drought, and one at midday to see what the total water stress is. Values that are statistically different from each other are marked with asterisks above them. Cottonwoods are shown in blue and Russian olives are shown in tan. In the graph, we can see a lot of variation in water potential from month to month, which indicates a strategy change in water use as the growing season gets hotter. The pre-dawn shows that both species are experiencing drought because the water potentials are still negative even when the sun isn't out and the air is the coolest. During the midday, water stress is the highest from the heat of the sun, and that is demonstrated by more negative water potentials. From the midday measurements, it is evident that the collected data suggests that Russian olive trees change their water use in statistically significant ways depending on the environment it finds itself in more drastically than cottonwoods do. So the implications of this data are important, especially when analyzing context of anthropogenic climate change. Climate change threatens riparian ecosystems because more frequent droughts and disturbances paired with increased heat and radiation damage. Because of the relative adaptability of Russian olive trees compared to cottonwood trees, they may be able to push out the native cottonwood trees entirely if they are better suited to survive the harsh conditions associated with climate change. The study is still ongoing, needs more longevity to be considered definite. The data collected so far points to that being true. And my sources are linked there, and I can take some questions now.
Question here.
I couldn't see. More plastic just means that the plants can change their phenotypic expression, i.e. their somatal conductance, so how open their stomata are in response to water stress, and so they can limit the amount of water that's being evaporated when they do photosynthesis at different times. Yes. Yeah. They can use more water, or it can use less water. That's just it, dependent on the plant's physiology. Each one is different just based on the species it is. But most of them respond to the environment in the same way. But what we found specifically with this is that cottonwood trees and Russian olives have different strategies. Russian olive tend to close them more often than cottonwoods do, and cottonwoods just kind of keep them open the same amount of time. So,
Excellent. Thank you very much. Perfect. Okay, so at this point, that That rounds out all the presentations for today. I'd like to give all the student presenters a round of applause, a really topically diverse set of presentations. Okay, and so at this point, so that everyone who's going to be voting in the audience, and one thing I'd like to say at first, so we're going to now vote using this Mentimeter system, we really only want those people who've been here for all the presentations to vote. So if you showed up like 5 presentations in, I'd ask just please refrain from voting. But before we do that, I'd like to have each presenter come up in order 1 through 10 and just state your name and also just your title, if you remember the title of your presentation exactly, or just give the topical, remind everyone what your presentation was.
Austin Clark, using heat and microcensus data.
I'm Riley, and mine was polar bears in a warming Arctic.
I'm Autumn Hartley, and I was doing a preliminary assessment of carbon storage in the North Atlantic.
I'm Lucy Leary, and I was studying how power law noise affects ecological long transients.
I'm Julie Moyano, and mine was ranching amidst drought, an analysis of traditional ranchers in Baja California Sur, Mexico.
I'm Nathan Murphy, and I did a satellite telemetry study of booted and steppe eagles in the African Eurasian flyway.
I'm Kyler Pack, and mine was on wharf accuracy during temperature inversions.
I'm Jacob, and I talked about modeling valley fever.
I'm Talon Townsend. I did explaining PM 2.5 values using random forest and explainable AI.
I'm Brant Wynn. My research is on the water use of native versus invasive species in riparian zones.
Excellent. Okay, so here's how it works. We have a QR code we're going to put up on the screen here, and then you'll have the option of selecting 3 presentations that you're most excited about out of the 10, and we'll do 1 round of voting, and we'll see where in real time where the votes land, and that's how we determine the winner. Again, if you came in late and you haven't seen all the presentations, please don't vote. Thank you. It doesn't look like many more votes are rolling in at this point. Okay. So do we have 3? Do we have 3 like winners that get selected here? Please remind me. Yeah, we have cash prizes for this. So Jacob, Julie, and Nathan are in order of 1, 2, 3. And I believe all of the winners need to report down to the table downstairs, or it's you specifically. Awesome. Congratulations to everyone here. The presentations are awesome. I really enjoyed this initial year of these student research lightning talks, and congratulations to the winner and all the winners and all of the presenters. Thank you very much, everyone, for attending.